questions before we get started?
When's our first test again?
First test. Pull the calendar up because I like having something to point at. First test is coming up soon. Today is February 7th, and the first test will be administered during lab time on the 19th, 20th, or 21st, depending on which day you normally come to lab. So it is coming up in about 2 weeks. Now, I'm glad you asked. What that means for lecture is, this week we're covering momentum and collisions. Next week, we're at least going to spend the start of the week talking about energy, and then how it ties back to everything we've already been handling. And then the tail end of that week, as well as all of lecture the following week, or at least these 2 lectures the following week, will be dedicated for test review time. What that means is, I will make sure that everything that you could possibly need to know about the test is made available to you. I usually put up a list of concepts that you should know before you take the test. Again, you should also be doing all of the homework for each of the relevant chapters. Test 1 will be on chapters 1 through 7, which is everything from the beginning through next week. I'll also be updating the formula sheet that every student gets to use. So again, you'll have a formula sheet on said test. You should definitely be doing the homework as practice. And again, I post the answers to the homework. It is just practice, because a non-zero amount of the test questions are homework questions again. So if you've done them on the homework, you'll be in very good shape. So think of the homework as the practice test. Sound fair? All right. And again, I give the test during lab time. So, 1:30, whichever of these days you normally come to lab, you would come here for the test instead. I write it as if it's to take 1 hour, but you have up to 3. And that also means lecture that week, or at least these 2 days, is dedicated to just studying. So lecture will be about answering questions from you guys, making sure everything makes sense and feels all right. Does that sound fair? Okay. So what you guys should be doing is, again, reviewing notes, doing the homework. If you can do the homework, you'll be good on the test. And my goal would be to have it back and graded by that Friday. Any questions, concerns, complaints?
How long is the test?
I write it with the intention of it taking you guys an hour. Basically, if it takes me about 15 minutes, it'll take you guys an hour. And even then, you still have the full lab time to do it in anyway. Like, I don't stop you at an hour, you can keep going, because I'm gonna be here anyway.
Are you gonna be here, but you won't be on the Tuesday?
I won't be here on Tuesday, no, but Dr. Edwards will be instead. He is under the same instructions. Answer questions, help people out. Proctor for the whole 3 hours, or until everyone comes. Usually about 10 to 12. Some of them short answer, some of them math, so it's a mixture. One of them will always be pick the laws of motion out of this lineup. So again, you do have to be able to identify the laws of motion. I'm also usually in the habit of making a practice test, which is just more practice questions. Again, you should think of the homework as the practice test, but I'll post some more of my own design as well. Does that answer the question? Okay, bless you. Anything else on your minds right now? And I'll mention again, in case it wasn't clear at all, test is open formula sheet. I'm going to be finishing up the course formula sheet shortly so that you can familiarize yourself with it in the coming weeks. It'll have every formula you'll ever need for this class on it, and any constants and things that you need to know. You don't have to memorize any formulas or any numbers for this class. Also use your calculator, and I encourage you to ask whoever's proctoring, me or Dr. Edwards, questions. I want to make sure you, at the very minimum, understand what's being asked of you. Sound fair? All right.
Any conversions after the week?
Yes, any conversion factors needed will be given to you. Also, because I don't think I've mentioned this out loud yet, there are built-in bonus points. I don't like doing one bonus question, because if you don't know it, then you don't get to benefit. Instead, there's just more points than you need to get a 100. Like if it was if it was a 10-question test, some of them would be worth 11 out of 10 instead of 10 out of 10. Anything else on your minds here at the start? All right. Now, on Monday, we talked about Newton's third law of motion. That will be relevant today. We also started looking at momentum. We defined what momentum is, looked at the basic definition and formula for momentum, that being measurement of how difficult something is to stop. Momentum equals mass times velocity. Again, this rho symbol is the momentum. It's a vector, it's measured in kilograms, meters per second, because we never gave it its own dedicated unit. And the more of this thing that you have, the more difficult it is to bring you to a complete stop. That can be because you have a lot of mass. Again, a train moving at any speed is not easy to halt. But it can also be because you're moving fast. For that reason, a fast thing with a lot of mass is nearly impossible to bring to a complete stop easily. Again, Now, some things to note about momentum as we continue describing it. Momentum's kind of weird in that it's one of those physics concepts that you can never really observe directly. You can't look at something and see the momentum in it. It doesn't like give off an aura that tells you momentum is present. You can only really observe momentum when something has it and is using it to move, right? This is one of those physics things that we can only measure indirectly, kind of like energy and heat and things like that. So momentum is weird because you can't really see it. You just see that matter is moving, therefore momentum must be present. But it can also transfer between objects. Objects are capable of changing their momentum levels by either having something add more momentum to them or by having something take that momentum away, kind of like electricity almost. You have more electricity, you can do more stuff, but you can also run out of it. So momentum levels can change. And I'm hoping that makes sense conceptually because you know that velocity can change. Things can speed up and slow down, correct? And when that happens, your momentum level would also change. If you plug in a different velocity, you get a different momentum. So if you speed up, you're gaining momentum from somewhere. And if you slow down, you are losing momentum to something. The act of changing momentum, either gaining or losing, this is a new vocab word, is called an impulse. The definition of impulse is a change in momentum, kind of like how the definition of acceleration is a change in velocity. So it's just a vocab word for describing something that should sound familiar. Definition of impulse is change in momentum. And the easiest way to change something's momentum is just to change its velocity. Again, if you make something go faster in a direction, you're giving it more momentum, and if you're slowing it down, you're taking its momentum away. So changing something's velocity is a change in momentum, and that is called an impulse. How's that feel for just as a vocab word? All right. Now, we measure impulse by finding change in momentum, and somewhat frustratingly, physicists decided a while ago that just calling impulse delta rho for change in momentum wasn't good enough. You can use delta rho for it. I'm going to call it delta rho pretty often because this is literally change in momentum. But some physicists decided this wasn't good enough. They gave it its own symbol, separate. And that symbol is J. That symbol is J because we ran out of English letters a long time ago. The letter I is used for something else. Lowercase I is the imaginary number. Uppercase I is electric current, weirdly. So they gave it a J instead, a lowercase j, which, I mean, is almost a lowercase I, kinda. It's a weird choice in my opinion, kind of like how rho is a weird choice for momentum. And you don't have to use it necessarily, but I want to make sure you're familiar with what the J means if notes you're looking at or the book uses it. If it helps, you can call it gym pulse. Gym pulse and rho momentum. However you want to describe it, J or delta rho, easiest way of calculating impulse is just mass times change in velocity. Velocities change all the time, way more often than mass changes. Mass never changes just spontaneously. Matter doesn't just vanish or manifest out of nowhere. So most often, the best way of calculating impulse is mass times the change in the change in velocity of an object. But there's another formula that can describe it. Force times time. This is basically 3 different formulas that I've run end to end. I'm going to rewrite them all separately for a sec just to make that clear. Impulse is change in momentum. Impulse can be calculated by taking an object's mass and multiplying it by its change in velocity. And the third way of calculating impulse is by understanding that some amount of force has to act on an item in order to be changing its velocity. Because we know, again, comparing all of this to Newton's laws, we know that force causes acceleration from Newton's second law, correct? And what is acceleration but a change in velocity? So force causes impulse, and if you're undergoing an impulse, your momentum is changing, odds are your velocity is also changing. So this is the force acting on an item that is going to cause its momentum to change, cause its velocity to change. So force causes momentum. Sorry, rewind. Force causes impulse. I got too many vocab words in my head. Force causes impulse. Force causes acceleration, therefore it causes impulse. Changing momentum. So 3 different ways of saying the same thing. Again, in physics, we like to use math to describe the universe. We use math as a language. This is the same sentence written 3 ways. You know, the dog runs, the dog walked fast, the dog got there quickly. 3 ways of saying the same thing. Conceptually, how are we feeling so far? All right. So, impulse, feel free to just call it delta rho, but some places it's going to be J. It's still a vector. Like the change in a vector is still a vector, and momentum is a vector. So a positive impulse means you are gaining forward momentum. A negative impulse means that you are losing your forward momentum and instead gaining backwards momentum. So impulse is still a vector because momentum is still a vector, and this is just the change in momentum. And since it's just the change in momentum, it has the same unit as momentum. It's still kilogram meters per second. Now, with all that said, since this is technically a couple new formulas, let's practice them. Look at some situations where they are applied. And to anyone who enjoys sports, I'm about to ruin them for you. It turns out most sports that humans have invented are applications of impulse. Because most sports involve hitting something with a stick or getting something from point A to point B. Therefore, you have to exert force on it to change its momentum and turn it around, one way or the other. Most sports are secretly about impulse and also torque. I'll talk about that in a few weeks. So let's do some baseball math today. The numbers present in this situation are, I believe, accurate to feats of the actual Babe Ruth, just converted into metric for simplicity's sake. So we are going to pitch a baseball at this guy. Regulation baseball has a mass of 145 grams. So that's the mass of the ball. Got the variables needed listed here with their correct symbols. The mass of the ball is going to be 145 grams. And our pitcher is going to throw it at Babe Ruth at about 90 miles per hour, which converts to 44.7 meters per second. Again, fairly standard for the metric version of baseball. Now, in sports, again, humans tend to use a stick to hit a thing. So the baseball bat is going to hit the ball and exert some amount of force on it. We don't know how much. We'll figure that out later. And the bat is going to be touching the ball for a certain amount of time. That will also be important later. But the thing to note first, the thing that you tend to watch baseball for, is that the bat, Babe Ruth is going to use the bat to turn the baseball around. The baseball approaches Babe Ruth at 44.7 meters per second, swings the bat, exerts force on the ball. Now the ball is moving at 69.4 meters per second in the opposite direction. That's important. I've got here drawn out very poorly handled pictures of the before state versus the after state. Yes?
So the initial is like when the pitcher throws it, and then the following is after he hits it.
Correct. My two images here are before impact with the bat and after impact with the bat. Before they ever touch versus after the bat is done and they aren't touching anymore. Does that make sense? Okay. This train of thought is going to be similar for all collisions, because this week, like today and Friday are going to be about collisions, as is lab next week. This is basically our first collision question. The ball and the bat are going to collide, exert force on each other, exchange momentum with one another. Every collision has a before state and an after state. Again, we'll get in the habit of thinking this way this week. So again, this is the ball's initial velocity before it ever touches the bat. Bat does its thing. Now the ball's moving that way in the opposite direction. And we have a few things to solve for given all this information. Any questions so far on just the premise? A minor historical footnote. This return speed on the ball after Babe hits it would convert to like 130, 140 miles per hour. So again, if these numbers are pulled from the history books, very good baseball player. So, first question. What are the initial and final momentum, technically the plural of momentum is momenta. What are the initial and final momenta of the ball itself?
Would the initials be how fast he threw the ball?
Yes, well, momentum initial would be its momentum when it, as it's thrown before the bat hits it. So it's momentum in this moment, before the bat touches it. How much momentum does it have here? And then separately, how much momentum does it have here? So given what we know, again, there's 4 numbers presented to us so far. given what we know about the ball, how do you feel like we should best find its initial momentum before impact with the bat? Sorry, a little louder.
Never mind.
It's okay. I only ask because you're right.
Multiply the time times initial. That's what I said, initial.
Oh, sorry, time? Time times what?
The initial, 44.7%.
Almost. Sorry. Almost. I apologize. My ears weren't working very great. But that's close. We do need this number, because this is its initial velocity. It has a certain amount of momentum that gave it this velocity. What do we do with it?
Multiplied by the mass.
Multiply by mass. Momentum is mass times velocity. That is its definition. And if we want to find initial momentum, which I've called here rho I, momentum initial, we want to make sure to use initial velocity rather than final. And you always want to be, I encourage being specific with your variables and labeling them to make sure that they are distinct in your own head. So, we know the ball's mass, we know its velocity. Do we want to use 145 grams in our math? No. We always like kilograms in our formulas, evidenced by the fact that the unit for momentum and impulse is kilogram meters per second. So how many kilograms is 145 grams? I'm saying 55 all the time. Sorry, a little louder. It's actually 0.145. Kilo is 1,000 times bigger, and 1,000 is 3 zeros, 3 decimal place jumps. Again, please feel free to write both in your notes and on whatever formula sheet you'll use for the test. King Henry died by drinking chocolate milk. If we're going from base to kilo, decimal point has to hop 3 times to the left. So that would take us to 0.145. Again, massive, should be the metric mass of a league baseball. And my memory serves, that should give us about 6.48 kilogram meters per second. Does anyone's calculator disagree? All right. So that is the ball's forward momentum before anything changes. The pitcher throws it, that's how much momentum the pitcher gave it, that's how much momentum it has until the bat changes that fact. Now, we can do the same basic thing to find its final momentum, you just want to use its final velocity instead. So the ball hits the bat causes its velocity to change. If we're looking for its final momentum level, you take its unchanged mass, because mass doesn't just spontaneously change, and multiply it by that final altered velocity. And mass is the same. The only reason the mass would change in baseball is if the impact ripped the skin off, which I guess can happen, but we're going to ignore that for now. And the final velocity, 69.4. Note, this velocity points in the opposite direction as the first one. That tends to be the point of the pitcher and the batter in baseball. Ball starts one way, batter wants it to go the other way. So the change in direction is important, and we need to note that. Ball was moving to the right, now it's moving to the left. You have to indicate that by putting the opposite sign on there. It's now heading return to sender, or I guess hopefully over the sender's head. And so that will give us a different, bigger, more negative answer. Momentum final, again, if my memory serves. Please let me know if your calculator disagrees with me. Negative 10.06 kilogram meters per second. All right. So two different momenta for the two different points in time here. We've got initial versus final. And something had to happen to the ball in order to change that momenta. Namely, again, the bat hit it. But just as initial versus final, how I feel so far. All right. Next question, given all the information that we have and have just found, what must the ball's impulse be in this interaction?
Wouldn't it be like negative 3.53?
Almost, but you're on the right track. Would it be accurate to say that you just tried subtracting the two numbers to represent the change from one to the other? Yeah, exactly. The definition of impulse is change in momentum, and we know the initial and final momenta, so we can find the difference between them. You're absolutely correct. That's why I asked for those two momenta first. Now, delta anything is always very specifically final minus initial. So I'm going to rewrite that as such right now. Impulse is change in momentum. Delta anything is final minus initial. That order and the negative sign are going to become relevant. Now this order tells us we have to write the final one first, and the final one is actually the negative one since the ball turned around. So the first thing to go in here is actually the negative 10.06. And then we subtract the initial from it. So that means that we are subtracting the positive 6.48. And this order with those negative signs, rather than giving us, the 3 point something, is actually going to give us 16 point something, but specifically negative 16 point something. Negative 16.54 kilograms per second. The negative on this answer means that the impulse, the vector impulse, points to the left in the negative direction. The momentum of the ball has become very strongly in this direction, whereas it was initially in this direction. This, again, the function of the bat in baseball is to make the ball turn around. And you need to have a big enough impulse to take all of that forward momentum, get rid of it, and replace it with a bunch of backward momentum. So that is why this answer is, at least its magnitude is bigger than the other two, and the negative sign tells us that all of that impulse points that way. Your left, the way that I drew everything. How does that feel? Question? So that is, in fact, the impulse of the ball. My last question, again, given what we know and what we have found, how much force does Babe Ruth via the bat apply to this ball? How much force is involved in this collision? much force does the bat have to exert on the ball to make this happen?
It would be like the difference between 42.7 and -16.
Well, that difference would tell you the change in velocity, which you could use to find impulse, you could use to find acceleration. Because if velocity changes, then you are accelerating, correct? And there has to be some amount of force present to cause that acceleration. We know this, again, from looking at Newton's second law. Net force equals ma. So the force from the bat acts on the mass of the ball to cause the ball to accelerate. And we know we accelerated because the ball's velocity changed, because it underwent an impulse. Now there's actually a couple of different ways you could go about finding that force, and I'm actually going to refer back to this formula in a minute. The first thing I want to do, though, is draw your attention to the third part of the impulse formula that we haven't used quite yet. I wrote them in this order for a reason. Impulse is caused by a force acting on an object for a certain amount of time. That force is going to cause the object to accelerate. But it has to act in a specific time frame in order to get it to a certain speed. Because every single collision, and again, collisions is going to be what we're studying kind of all like in lecture for a few days and also in lab next week. Every collision lasts a certain amount of time. And in this case, I've already told you what that time is. This is the number of milliseconds the ball and the bat are touching. Every collision lasts a certain time frame. Even if it's too fast for you to really consciously notice it, they all do. And again, I watched a lot of Mythbusters growing up. They tend to crash a lot of things into each other and record on high-speed cameras so that they can watch how many frames pass between start to finish, how many seconds pass from start to finish if they were, again, like running a test car at a wall or something. In this case, that is the number of milliseconds that the ball and the bat are touching. Therefore, that is the amount of time that the bat had to exert force on the ball. So the bat's force times the time that the bat is acting on the ball is also equal to the ball's impulse. And this does still connect back to Newton's second law. Again, I'll show this on the slides in a moment, but this is still ultimately about Newton's second law. Turns out this formula is the same thing. But right now, we've got the impulse, and we know how long the force acts, so we can use this to find that force, the force that the bat hit the ball with. You gotta keep that negative sign on there though, that's important. All right so far? Okay. Do I want to plug in 0.71 milliseconds? No. How many normal seconds is 0.71 milliseconds? How many zeros? Sorry.
Like 0.02. What is it? 0.007.
You guys are on the right track. I'm going to refer you back to King Henry Died By briefly. If you're going from milli to base, because without no prefix is the base unit, you got to jump the decimal point 3 times to the left again, 3 times. So that's going to go from 0.71 to 0.00071. 3 hops to the left. Milliseconds are tiny, and this is less than 1 millisecond. Most collisions don't last very long. Again, the human brain, when you see one happen, it may as well be instant, right? Like if I even just drop this golf ball on the table, you know, it goes from downward to back upward almost instantaneously to our senses. It's because it's a very teeny tiny amount of time. Does that make sense? It is a number, it's just usually like less than human processing speed in my experience. Now what I want to do with that teeny tiny number if the goal is to solve for f?
It's the time.
Divide both sides, very good. So that means negative 16.54 over 0.00071 equals f. And that is going to give us a whopping 23,295.77 approximately newtons of baseball bat impact force. If you're not used to thinking in metric yet, for scale, that's about 5,000 pounds. Baseball bats are no joke. Also, I guess this guy was no joke. So that is the force that the bat has to exert on the ball in order to turn it around this much in that amount of time. Generally speaking, the faster a collision occurs, the less time it takes. The more dangerous it is, the more force is involved. Again, that's why in those test crashes that you might see on TV sometimes, I want to, disclaimer that. If you're watching a car crash test, the car tends to go from 60 to 0, faster than you can blink. That's a teeny tiny amount of time. That's a lot of force involved in that collision. The longer a collision happens over, the safer it usually is. If we divided by a bigger number, there'd be less force involved. Does that make sense? And that's why airbags do what they do. They basically lengthen the time it takes to come to a complete stop by padding the impact. The more time you have to slow down, the less force it takes. I'll also note, just as a disclaimer, even though Babe Ruth could hit a baseball with 5,000 pounds of force, he could not punch with 5,000 pounds of force or deadlift 5,000 pounds. I want to make that a clear disclaimer. Whatever you can do with a baseball bat is not the same as your deadlift. This man could not deadlift a car. The reason for that we will discuss in a few weeks when we get to torque. The idea is basically, though, when you are swinging a bat, you're using it as a lever arm and basically multiplying your output, but only at the end of the bat. So secretly, most sports are about impulse, but also torque, because most sports tend to involve hitting something with a stick. Baseball, golf, tennis, things like that. Even, as it turns out, volleyball, football, and soccer are not immune to this because you can use your entire leg as a swing arm. Also in volleyball, it would just be your arms like this. So again, very impressive, but that does not mean that he could lift a car or shatter concrete with his bare knuckles. Just want to make that clear. He could shatter concrete with a baseball bat, but not his knuckles. Questions so far? All right. Now, let us tie all this back into Newton's laws, kind of the main point of the last couple of weeks. First, let's talk about Newton's third law. the action-reaction law. This is the force that the bat exerts on the ball. And note that the negative here means that that force pointed to the left. You need a leftward force to cause a leftward impulse to make the ball turn around and go to the left. So that's why this negative is still here. This is the force that the bat exerts on the ball. Newton's third law tells us that the ball must exert an equal and opposite force back on the bat. Question?
I was just gonna say, is that why sometimes when you hit the ball in the wrong spot, the bat shakes you or your hands?
Exactly. If you've ever done any amount of baseball, and this is an experience with me that turned me off of the game. If you don't hit the ball at a specific sweet spot on the bat, you feel that awful ricochet, that shaking through the bat that just goes up your arms and makes everything uncomfortable. And again, same can be true in any sport that involves hitting something with a stick. That happens because as the bat exerts force on the ball also exerts force back on the bat. And, you know, that force travels up your arms and into you. So that is exactly the source of that uncomfortable resonance in the bat. But even if you do hit the right spot and you don't get the uncomfy resonance, the ball is still putting force on the bat, and that's why sometimes in movies and also in real life, if someone swings the bat hard enough, it just breaks. Because the harder the bat hits the ball, the harder the ball hits the bat, and you know, at a certain point, the bat just can't take it and snaps. Similarly, sometimes the ball can't handle it, it just, you know, erupts into pieces. So they both exert the same force on each other. I want to make that clear. We're tying Newton's third law back into this. And technically, they exert the same force on each other for the same time interval, because they are only touching each other for that same small amount of time, right? You know, the time the bat is touching the ball is the same time as the ball is touching the bat. One can't touch the other longer than the first. Does that make sense? Same time frame. And that means that they received equal and opposite forces for the same amount of time. Force times time is impulse. So not only are the forces equal and opposite, the bat is going to get an equal and opposite impulse from this collision. Slight modification of the previous slide. All I'm asking now is, what is the bat's impulse? This is just an addition to the slide. Nothing else is different. What is the bat's impulse in this whole process? The ball would have to exert positive 23,000 newtons back on the bat, because this is what the bat did to the ball. The ball must do the same thing back, but with a rightward positive force instead. And that force times the same time interval would give you positive 16.54 kilogrammeters per second for the bat's impulse. In a collision, Newton's third law dictates that the two objects exert equal and opposite forces on each other, and it also dictates that both objects will undergo equal and opposite impulses. This is because the momentum in this entire interaction is conserved. There's only a certain amount of momentum present. And basically what the ball and the bat are doing is trading momentum back and forth. However much one gains, the other loses. The bat is giving momentum to the ball, which means the bat doesn't have it anymore. Or vice versa, depending on your perspective. So the two objects involved in the crash have the same force acting on each other for the same amount of time. Therefore, two objects involved in a collision have equal and opposite impulses as well. However much momentum one object gains, the other has to lose. Bless you. To tie this into Newton's second law, it turns out this entire time Newton's laws were about momentum, not just force of motion. When Newton was doing his work on this stuff, he was doing it about momentum. It was a momentum paper. So Newton didn't write this. Newton wrote this. Net force equals change in momentum over time. Now secretly, they're the same thing. Those two different versions of Newton's second law are the same thing. And I can prove it. Net force is mass times acceleration. Acceleration is change in velocity over change in time. If we just take this and put it in here instead of A, because A is this, so we're just combining our two formulas here. We get net force equals mass times change in velocity over change in time. And mass times change in velocity is change in momentum. So, net force equals ma is the same thing as net force equals change in momentum over change in time. Again, it's just two ways of saying the same thing. The wall is red, the wall is painted like apples. Just different weird ways of saying the same thing. And even further saying the same thing, all this impulse math I've been putting on the board is the same math again. Running out of board, unfortunately. Net force equals, bless you, by the way, change in momentum over change in time. What would happen if we moved time over here? Net force times change in time equals change in momentum. Well, change in momentum is impulse. So this formula is the same thing as this formula, which is the same thing as this formula. It's all connected. This is the conspiracy theory wall with all the red strings connecting it all. It's all the same thing. Which is especially why it's very important for you to ask me questions when you're confused. Because secretly we're talking about the same thing as 2 weeks ago. And if it didn't make sense then, it wouldn't make sense now. So again, please ask me your questions when you have them. In the moment you have them. It'll only get worse if you don't address the problem in the moment. So, secretly, Newton's laws have been about momentum the entire time. Nothing is new, as it turns out. And what we're going to do with all of this information is apply it to more collisions and to the phenomenon known as the conservation of momentum. This is just me setting up Friday at this point. I mentioned that the objects in the crash have equal and opposite impulses. However much momentum one loses, the other gains. Momentum's not destroyed, it's just transmitting between the two items. That's what we're going to prove on Friday. That's what we're going to prove in lab next week, as we actually run things into each other. Question? We do, yes. There is lab this week, therefore today, so do report the lab today. I'm just commenting on next week's. Let me know if you have any questions, needs, concerns, etc. Please have a wonderful day.